All right, so with regards to making points back on the exam, I actually had a much easier way for me and a much easier way for you to do it, which is that I'll select one of the questions on the exam, and I'll probably give it or a similar question from the first exam on the second exam. I'll let you know which question it is on the second exam, and if you get that question, and that will replace the score you got on the first exam for that question. So it's one that I'll choose something that a lot of students got wrong. So there will be a question from the second exam that basically that you can redeem. Okay. Or I might make it so that it's choose one of two. So, now I did say that we were going to start regular expressions today, but I actually I was trying to figure out what was a good assignment based off the statistics that statistics stuff that we've been doing so far. And I actually found one from a while ago that I had remembered and wanted to do. So next week, we're going to continue on with the statistics in the dictionaries today, but we're going to do it in a bit more of an entertaining manner by talking about dice rolling and stuff, because we're going to start talking about basic games. Very basic games and theories about games. So, and we're going to start off by talking about another paradox, just like Monty Hall is a paradox. And again, what we're going to do is to show that basically that we're not crazy. We're going to have the computer simulate it for us. Okay. So, we're also going to learn a bit about sorting today and other things. So let's. All right. But yeah, we're going to talk about dice game, and your next homework is going to be a dice game called Pig, from 1940, which is a game from 1945. It's a very fun game, and there's a lot of things we can do with it, and I was playing around with it yesterday. So, but first I want to talk about another paradox, right? I mentioned something that basically that it's very likely that two people in this classroom have the same birth date. Have the same birthday. Not the same birth date, which, not the same year, but the same birthday. That's called the birth, and that seems unlikely. After all, there's 365 days in the year, right? So the likelihood that I have the same birthday as somebody else in the class, right? They'd have the same. It seems pretty unlikely. But we're not asking, do you have the same birthday? We're asking, does some pair of students have the same birthday? And it's actually extremely likely. So the birthday paradox, okay, come on, there you go, birthday problem, where the birthday paradox concerns the probability that n people randomly chosen, that some pair of them will have the same birthday. By the pigeonhole principle, which is this really silly name in statistics, it's a 100% probability that two people will share the same birthday when you have 367 people, because there's only 366 possible birthdays, right? You've got 365 days in a year plus the leap year day of February 29th. So what the pigeonhole principle is, this thing in statistics you'll learn about if you take statistics, but it's a very simple saying, which basically says, suppose you've got a bunch of pigeons and a bunch of pigeonholes. If you've got more pigeons than pigeonholes, then two of those pigeons are going to have to share the same pigeonhole, right? So it's basically saying, hey, if we're trying to see if we've got a duplicate or something, but there's only so many possibilities, right? If you have more things you're checking than you do possibilities, then one of those possibilities is automatically a duplicate, right? So let's just assume there are no leap years, right? There's only 365 days in the year. You have 366 people. It's possible for the first 365 to all have all different birthdays, but once you have that 366th person, he's got to share a birthday with somebody, right? Everybody tracking with me so far? All right. So, however, what's interesting is that there's a 99.9% probability that 70 people that if you've got 70 people, then 2 of them have the same birthday. And 50% possibility was just 23 people. So I'm very sure that the people in this class, that somebody in this class has the same birthday as somebody else. Okay? And it's surprising, but what it is that basically you're checking you're making a bunch of comparisons here between the number of people. So rather than getting into the statistics and all this numbers, which make your eye bleed, or something like that, we're just going to simulate it, okay? Makes sense? We can kind of simulate this to see if we're correct. Okay, so what we're going to do is I'm going to create and again, what we're going to do is use random numbers to simulate this. Okay, so birthday paradox, right? Which is as follows. Now, there's a couple ways I'm going to have. So the main difficulty we're going to get into is how in the world do I keep track of this? But what I'm going to do is, let's go with just 23 people, okay, like the example says. Import random, right? To generate a random birthday, all I have to do is def generate birthday. I'm not gonna I'm not gonna make it hard for me. I'm gonna also do this properly with functions now, unlike I'd been doing previously. To generate a birthday, right, all I have to do is, this is a simple one, return random dot rand range 1 through 365, right? I'm not going to try to do like April 2nd as a birthday or November 5th or anything like that. I'm just saying there's 365 days in a year, right? So give me a number from 1 to 365, with 1 being January 1st, 365 being December 31st, 2 being January 2nd, and you can figure out the rest from there, right? We're using day 1, 2, 3, 4, 5, 6, 7, of that. So this will just simply generate that, and generate birthday will make a bit more sense in our code. So let's go with generate. So we could do that. Def generate birthday lists. A birthdays list. So this will generate an entire list of birthdays. Okay? And I'm going to say over here, num, where num is the number of birthdays we want. So I'll comment it. Generates, typing's a bit difficult for me right now. I cut my finger with a knife yesterday. I did that while cutting a bagel. I wouldn't say necessarily that it was worth getting cut for the bagel, but afterwards I definitely feel like I earned that bagel. So let's see. So forgive me if I'm a bit slow with typing today. So generates a list of birthdays of num birthdays. So here we're going to have birthdays be an empty list to start out with, okay? And this is just simply because I'm just doing this and splitting it up into functions and stuff. And all I'll do, and this is also to remind you of the different function calls that we can do, right? So and what we want to do, we want to generate a single birthday and add it to the list, right? It's always easy to think about if you're not comfortable with loops. Just think about, okay, how do I do it for a single one? To generate a single birthday and add it to the list, we go birthdays.append, and then we can actually just directly call the function generate birthday, right? We can do it like that. And then all we have to do is just say we want to do that amount of times. For blank in range num. This will generate this a certain number of times, right? Make sense? And then return birthdays. Okay. Def main. And what we can do over here in main is now say, and then I'll call main in the end. Okay. What we can do over here in main is just simply say birthday list is equal to generate birthday list, right? Notice I've given it birthdays over here, but it's birthday list over here. That's perfectly fine. And we want to generate 23 of them. It's not going to do anything really, or it doesn't seem to do anything because I didn't print anything out. So we're going to print out birthday list and see, do we get repeats at all? Is anything repeated? And that's a bit hard to tell in here. So what I'm going to do is that I'm going to sort that list to make it a bit easier to look at. Okay? So the way we sort things in Python is fairly straightforward. We use the sorted function. Which is a function built into Python. Sorted birthday list. And you can use that on any collection. And what that will do is that returns a new list. That's what I was testing there. It returns a new collection, but now it's sorted. And you understand what sorted means kind of instinctively. Sorted means sorted. Oh, look at that, a duplicate. 132, 132. Okay. Sorted means that the numbers are put in order from lowest to highest. 36 is repeated again. 95 repeats. Remember, we're not generating these in order. We can, in fact, I'll print out it before we sort it and after we sort it. Looks way more random when we do it like this, right? Looks like this. This looks like a bunch of random numbers, but when we sort it, oh, look at that. Two of them match. 342, 342. That's kind of weird, ain't it? Kind of spooky almost. I mean, it is getting close to Halloween. By which point, speaking of Halloween, I do have to mention that we will most likely not have class on Halloween because I will be going, I have a wedding to attend on Halloween, and it's in Georgia.
That's a spookiest wedding.
They're great. They're interesting friends, and this is a wedding where the bride's wearing black. So you know, and but they're great friends. It's actually a costume. They actually demand that it's required that everybody shows up in costume for that wedding. And I'm going in planes, trains, and automobiles, or rather, my family is. So I'm going as Speed Racer. So anyway, suffice to say, I will be driving down to Georgia on Wednesday. So next week. So yeah, this is the important bit. Next week on Monday, I will be. I'll switch my office hours to be on Monday next week, so that instead of being on Wednesday. And then we'll still have class on Tuesday, and you'll still have lab that week. Too bad, sorry, but Thursday probably we most likely won't have class. So rejoice. And I will, and you can still send me emails, and I'll still try my best to respond to them because it's not like I would say it's not like I'm going out to the middle of nowhere, but Wednesday night we're stopping at my wife's parents' place, and that is on the South Carolina-Georgia border, which is pretty much in the middle of nowhere, and God help me if I try to upload any videos there. Okay, anyway, so back to our spooky problem. Now, the reason for this paradox, why are we getting so many matches, is that really what we're doing is that we are not checking just does one person have a match. We're checking 23 pairs of people have a match, right? we're checking basically so, you know, we basically check, but this is actually, again, you can check the statistics here if you're interested. But basically, we're checking if a lot more people than just two, we're not checking one person against 23 other people. So we're not checking 22 people. We're not checking 22 pairs of people. We're checking 22 pairs of people and then 21 pairs of people, right? We're not just checking does 321 match all these other people. We're checking does 180 also does 180 have a match, and then does 261 have a match, and then does 269 have a match. So we're checking 22 pairs plus 21 pairs plus 20 pairs, and that ends up being a lot of pairs. Specifically, how many pairs would that be? It's what we call a triangular number, to be honest. But we kind of just calculate that with def count pairs. Now, the big thing about this is that, remember, a pair of people is, before I finish this, count pairs, pass. A pair of peoples is reflexive. It's reversible. Alice and Bob is the same as Bob and Alice in terms of comparing people. So we're so 50 and 140 is the same pair as 140 and 50. So what we're going to do is that we basically have to use a nested for loop to count this. So count pairs, birthdays, right? And what we'll do is that we'll say for and here we have to use the indices because we're going to be using the indexes. So for index in range, for index in range, for start index, because I don't want to necessarily use I and J because that makes makes people go crazy. So for I in range of length birthday, so all the valid indices in birthday. So we'll get birthday is equal to start index, or not start index, but birthdays. Oh, and here I totally messed that up. Len birthdays. Birthday is equal to birthdays dot start index. So grab the birthday, the first pair. And then for index in range, and here's what's tricky. We're gonna do it we're gonna go up until length of birthdays, sure, just like we were doing earlier, but our starting point is gonna be different. Because we only want to check birthdays to the left of us, to the right of us in our position. Show what I mean by that. Pass for length and range, start index plus 1. Again, I'll run this just again. We only want to, so if we're currently at 136, right, we only want to check if we're currently at 134, we only want to check stuff to the right of 134. Now, the reason for this is that 96, we would have already checked the stuff before. The stuff in front of us would have already checked us, right? 96 would have checked 20, 21, 53, 134, and all the rest. 20 would have checked 20 and 21, 20 and 53, 20 and 134, so we don't have to check 134 and 20, right? We're checking the number of unique pairs here, right? So num pairs is equal to 0. And then pairs plus equals 1. return pairs. So we can check. So print count pairs. Actually, I'm going to check it for 5. Sorry, for 10. How many pairs is that for 10? Should be 55 pairs for 10. Birthday list. Local variable pair. Oh, num pairs. I'm really all over today with these names. Num pairs. Run. 45 for 10. Then 11 should be 55. Yeah, that makes sense. Okay, so we've got plenty of pairs here, is the point. So a lot of pairs. So by the time we get to 23 pairs, by the way, by the time we get to 23, that's 253 pairs. In other words, we're checking 253, we're doing 253 checks out of a possible 365 possible birthdays. So, of course, we want to actually now, but we don't really need to care about that too much. What we do want to care about is how do we have to get the computer to automatically tell us if there's a match? Def has duplicate birthdays. Okay, so we're gonna this is gonna be the main thrust of the next like 10 to 20 minutes. This function. Everything else was just simply leading up to this function. So suppose we have our birthdays. We want it. This function will return true if there's duplicate birthdays and false if there's not. Birthdays. Okay, so how can we check? The first way is that we can just simply go through like we did there. So the first way is basically use this function up here that we had. Copy. I'm going to erase this pretty soon so you don't have to worry about copying it because this is not the easiest way to look at it. It's the most time efficient way. It's not even the most time efficient way to do it actually. So, and what you can do is just simply say, hey, if return false. So return false if I can't find any birthdays that match, but if num pairs, but if not num pairs, so here we don't need to care about num pairs. Other birthday is equal to birthdays. Again, this goes through all the pairs. Birthday dot index over here. If birthday equals other birthday, so if those are the same, then we found a match, return true. Make sense? So what we can do is say, hey, print has duplicate birthday, what did I delete? Oh yeah, I forgot, I deleted this. Birthday list, I'll just call it birthdays from now on. Birthdays is equal to generate birthdays list, 23. Generate them. Birthdays is equal to sort it is equal to, actually all I'll do is I'll just simply say, I'll print it. Print has duplicate birthday, pass it in, birthdays. Main has invalid syntax. No, definitely don't do a return false. Definitely don't do a return false in the else statement over here. Because otherwise you're just simply checking the first pair. Basically, you'd be returning too soon. So what is the invalid syntax? Where? In me. Oh, yeah. Let's see. So false, that doesn't have a match. True, false, true, false, true. This one has a match, so which is the match? Gee, wish it could tell me which one was the match. So, actually, we can do that. We can do that by returning a tuple. Python's unique in that you can return two things. That's a lie, actually. Python only can return one thing. It's just that the one thing can be split up into two things. Return true, birthday. Watch what I'll print out. False, true, 105. Notice that it returned it as a tuple. So it's returned actually one thing, but it's a one thing that holds two things. Make sense? So you can return multiple things in Python by putting a comma and just saying, here's the things I want to return. Right? So now I can print out and say, hey, we're returning true, and it's 152 that has the match. Oh, and they ended up being right next to each other. Okay. So another way to do that, a bit, which is also pretty good, is that we can sort it, like we did earlier, and use that sorted list, right? And the way we can tell, when we were sorting it, the way we could tell that it was, that we had a match with the birthday paradox, we had two of the same birthdays, is that when it was sorted, if two numbers were next to each other and they were the same, awesome. So we can use the same principle there. And then we only need a single loop. So we can do that with basically saying sorted list is equal to, and the reason I'm creating this is that I'm creating a copy of our list to sort. So I don't lose my original list. So sorted birthdays is equal to our sorted list. This will sort it from smallest to greatest. And then for I in, so this is a bit trickier, but for I in range birthdays, length of birthdays, and that's actually a mistake, but I'll fix it later. And what we do here is that we say, hey, if, we'll just simply call it left is equal to birthdays at I, and right is equal to, so we've got a pair essentially. And what we're going to do is we're going to do birthdays is equal to I, and birthdays is equal to I plus 1. Now I plus 1 we're dealing with lists is actually not that complicated. Plus, if we're at a specific index, I is the indexes I'm at, I plus 1 means one more, or more specifically, for the visual thinkers, one to the right. I means the one, y plus 1 means the one to the right. What would I minus 1 then be? The item to the left, right? The index to the left. I plus 2 is 2 to the right. Assuming we're viewing the list as basically this horizontal entity. So for each index, get the birthday at I, get the one to the right of it. If right equals left, right, and because it's sorted, we don't have to check any other pairs, then return true. And it doesn't matter if it's right equal left or left equals right. Again, return true, left. And no else false there, because then we'd just be turning the checking the first thing. The return false has to be, okay, we checked the entire thing and we didn't find a match, so return false. This will crash about half the time. So, yep. Well, actually, birthdays. This should still crash half the time. Index is out of range. Out of range. Range. Has a match. Always is out of range, actually. If right equals left. So it should be doing it sometimes. But it's showing me out of range. And the reason is that basically we're going through all the indices and we get to the last item and we say go 1 to the right on the last item, which is out of bounds. That doesn't exist. Make sense? Going 1 to the right on the last item. So the way we adjust that is don't go to the right last item. Go to 1 before the last item. False. 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 Oh, that's why it's not going. Because I'm not checking. I need to check sorted list. There we go. True, 85. True, 21. False. False. And this isn't sorted because that's the old list I'm printing out. I'm printing out before I'm checking for it. So, all right. So we could do this, we can generate some statistics on this too by basically saying how many matches there are, which we can do. Yeah, let's do that. So, def. So what we can do to generate statistics is we can do this a bunch of times in our main method. So, or actually, yeah. So let's generate this for blank in range. Let's do this 10,000 times, run this experiment 10,000 times, okay? And what we'll do is we'll keep track of our times. We'll call it hits, just for the time we get a match. Okay, and what we'll do is that we'll just simply generate our birthdays, and then throw this into a function. If has duplicate birthdays, and notice that I don't have to put a true here. I don't have to put if this is equal true. This will be true or false, so I don't have to really check it if it's against true or false. So if it has duplicates birthdays, I'm just going to simply switch this to returning just true. So if it has duplicate birthdays, hits plus equals 1. Print hits divide by 10,000 hits. Run it. So about half the time we're getting so just like the Wikipedia article said, about half the time we're getting a match, which is pretty cool. Right? But suppose you want to know a bit more than that, like quite a bit more. Okay, how many times am I getting 3 people who match? How many times am I getting 2 pairs of people who match? Right? That's really interesting information, right? Let's go ahead and I mean, again, if we check with 70 on this statistics, right, 2 people have this for birthday, it takes a bit longer, right? It was said above 0.9% when we have 70 generations. So let's go ahead and compute our statistics, but we need to be able to keep track of the data a bit better, right? The big thing is that with these, we're just keeping track of one piece of data. When we need to keep track of multiple things and count multiple things, this is when we want to use our dictionaries. So that's what we'll do here. So def count. Oh, what happened there? Okay. Okay, still recording this. Displays. Okay, now when I ask, or do we have displays? No, that's not at all what I wanted. It just hit out on me. Why in the world would it do that to me? Here we go. There we go. Mirror. Good. That's what I said. That's what I wanted you to do. Okay, count birthdays. So here we're going to be doing, we get our list of birthdays. And we're going to be doing a bit more, and what we want to do is specifically we want to count the number of times each birthday occurs. Okay? Now there's two ways to do this. I could create a list of size 366, right? That would be the indices 0 through 365. And I could just simply ignore the zero index, and then let everything, and then basically every time I see a birthday, increment the appropriate index. But instead, I'm just going to use a dictionary because that makes way more sense and is much more teachable. So, counts is equal to a new dictionary. Now remember, these are key value pairs. And the key is basically like an index. Only we get to decide what the heck the index is. Here it's going to be a number. And the value, again, can be anything we want. Here I'm going to be basically saying this is the number of times I've seen this number. So the number of times I've seen this birthday. So, for instance, so the way we do this is that we simply say for birthday in birthdays, or the singular and the plural. And what we use is that we use the in operator a whole lot. But this is the way that pretty much whenever you use a dictionary in this class, you're going to be using it. You ask yourself, hey, have I seen that birthday? If, or have I not seen this? So for birthday and birthdays, if birthday not in counts. In other words, if I've not seen it before, right? This is going to be the initial way that it is for every birthday. So if birthday is not in counts, in other words, have I not seen this birthday before? Have I not counted it yet? Well, I've seen it once, right? So I say that counts for that birthday is equal to 1. Right? That says if I haven't seen it before, well, no, I've seen it once. Else, I will have, it would be, otherwise, it's already there, right? If I haven't seen it before, then I set to 1. Otherwise, I've seen it before. So, what I'm going to do is I'm going to say the number of times I've seen it is going to be equal to the number of times I've seen it, but one more time. Make sense? We're just simply saying, and so now I will return counts. That's it. That's all I have to do to create a count. It's very, very simple. So let's go ahead and just comment this out for a bit because I want to just demonstrate what we're doing here. Okay, so birthdays, get birthday, generate birthday list. Okay, so here's 70 of them. And then print count birthdays. By the way, happy birthday if it's somebody's birthday today. So, suppose I should mention that. All right, and notice that basically what we've got here. Now, the thing about dictionaries is that they don't try to keep anything in order. So 43 had one birthday with 43, one with 313, one with one birthday of 314. 17 people of those 70 had 3 birthdays. That's what the 3 means. There were 3 17s in that set. There were also, by the way, that definitely means there was a duplicate. And also, 352 people had, birthday 352. So December, so that was sometime in December, had a match as well. So we are going, and then 336 also had a match as well. So we had a lot of matches for that. So we can start doing kind of statistics on this, using this in a bit more detail. First off, though, probably be nice if that was like, sorted in some way. So what are the different ways we can go through a dictionary? Counts is equal to, because we've iterated through stuff and put it into a dictionary, but we really haven't iterated over a dictionary and gotten stuff out of it. So counts is equal to, count birthdays. So let's see what happens when we iterate over it. For thing in counts, right? Well, for counting counts, but for print the thing in it. So what happens when I do that? It just simply prints out, what are these? The keys. These are the keys. Right? These are the birthdays. Okay? So that's the same as basically me saying this, by the way. For in counts.keys, this gets me the list of all keys. And if I want to get the values, I say values. And now it just iterates through all the values. So this one had 1, 2, 3, 4 people with the same birthday. Interesting. Okay. So, and then there's one last one we can use to iterate through. Items, which gets you the key value pairing. 154 had 2 birthdays. And then 130 had 2 birthdays. Okay, so that's useful. But the thing is that what I really like with this to be would be, I would like this sorted, right? So let's see if that works, though, if I do sorted around this. So what happens if I put sorted around just counts, right? Which should give me the keys. See what happens. There. It gave me those sorted. Dot valid. What if I do dot item? It will give me the key value pairs in order, which is great. So that's pretty cool. That will be useful for later. But now we can go through and start asking ourselves questions about the, we can start actually doing statistics on it. So we have a has duplicate. So let's go ahead and rewrite this for now that we're using a dictionary to do this. And what I'm going to do over here is a bit tricky, okay? Basically a way of writing a method but having 2 different options for it. So first off, I've just introduced a whole lot of concepts with one line. With just one argument, actually. Counts equal none. Right? This actually isn't too new. We've been doing this with print all the time. Just when we've been calling it, we've been saying separator equals this, or end is equal to this. This is what we call a default variable, which basically says, by default, this is going to be this. Right? If you don't give me a count, by the way, so I'm writing a function. It takes in birthdays. It's got to take in birthdays. No matter what, you have to provide birthdays to me. You have to provide something for me to do birthdays on. Don't care, but counts don't care. It's always going to be 1 if you don't give me anything. So for instance, if I do this, print counts, it would print out 1, always. If you don't provide something, that's perfectly fine. So, but if you do provide it, then you can provide 2 arguments. If you do provide 2 arguments, it will be set. It will be set to counts will be that second argument. Now, what I'm doing over here with counts equals none. None is a special keyword. You can see because it's nice, big, and red. None is exactly what it says on the tin. It is nothing. You can't add it to anything. You can't subtract it to anything. You can't make a function call on it. None is none. None is void. None is null. None means nothing. It means that there's nothing there. So what we can say is that if counts, really the only thing you can do with none is check if something is none. If counts is none, if you don't provide me a count, I'm going to do it the way we did before. And this is just so that we don't break any of the code we wrote earlier. So if you don't give me a count, I'll do it this way. Otherwise, you gave me counts, great. So I'll go through it this way. I could also make a separate function, which would probably be better, but I just wanted to introduce that concept. And I do mean introduce because we're probably not going to use it that much. And by not that much, I mean I don't expect you to see it on a test. And if I were to put it on a test, I'd put up a very explicit write-up as to what it does. One of the things I like doing on the second exam, by the way, is introducing a completely new concept on the exam and basically say, this is a foo. This is how you use a foo, right? This is the way to use a foo. Please use the foo to do this, right? It's one of the things I like to do. All right, so let's go ahead and check check counts for duplicate. This is what I'll do. I'll just simply have a new method because I don't want to necessarily confuse you too much. Check counts for duplicates. Okay. What we're going to do here is that we are going to say for birthday in counts, right? Birthday was the key. If birthday, so if the counts for that birthday is greater than 1, right? In other words, if we've seen more than one of that birthday, return true. Else, return false. Not else, return false. That's actually, I said, that only check the first one. So check all the, for every birthday in counts. If the number of times we've seen that birthday is more than 1, great. We found a duplicate, something with the duplicate. If we check all of them and none of them have and there's no duplicates, then we return false because there were no duplicates. So now we can change this to saying, hey, so we can change, and notice that was much easier to write than everything else. So for blank in this, generate birthdays. If, so generate birthday list, count birthday, counts is equal to count birthdays. If it has duplicate birthdays, if check count for duplicate, call it duplicates, and that's all I have to do for the code. Index out of range. Oh, count birthdays, check counts, not birthdays. There we go. Does the exact same thing, just slightly differently. But now we can also check, we can do something like this. def. Check counts for triplicates. Okay. How many times were there? How many times do we have 3 or more? So if there's greater than 2 for a count, right? And then we can do this one more time. We could do it like this. Quadruplet. We could do it as many of times. But we should but we can quadruplicates. Although this is getting a bit ridiculous with copying and pasting. So we'll generalize this out in a minute. But now we can say, we can keep, instead of hits, we can do is dupes is equal to 0, trips is equal to 0, quads is equal to 0, and then if it has duplicates, dupes plus 1. And you can pretty much imagine how it's going to go for the rest. Trips, quads, counts, and now we can do dupes divided by 10,000. 10,000 because that's the number of times I've run this. Trips divided by 10,000. And quads divided by 10,000. Run main. Run through it. So interestingly enough, when there's 70 people, there's a 99.9% chance of 2 of them having the same birthday. A 30% chance of 3 of them having the same birthday. Sorry, 31% chance of 3 of them having the same birthday. And a 1% and slightly more than 1% chance that more than one of them, so that 4 of them share the same birthday. That's pretty interesting. Okay. But how could I go up to ad absurdum with this, right? Right? If we had 365 people, right? Almost certain that they're always going to share a birthday. But how does that affect the other things? How would that affect 5 of them having a birthday? It's taking longer, by the way, because there's 365 people I'm checking, and a lot more counting to do. Right? You've got 365 people pretty much guaranteed that 3 of them are going to share a birthday. And 99.9% chance of 4 of them having the same birthday. That's pretty exciting and makes you feel not that special on your birthday anymore. All right, so let's go ahead and create a new function called check counts for, let's call it n-plicates, or we're going to actually call this count n-plicates. Because what we're going to do is that we're going to count the number of duplicates that we get. All right? And this is going to be a bit weird. Stick with me here. Okay? N-plicates, right? N being, 2-plicates, 3-plicates, 4-plicates, duplicates, 3-plicates, triplicates, quadruplicates. We don't know what type, though. But I really don't know what type, because are we getting 5-plicates? Septuplicates even? I don't know what we go at that point. So, I mean, God help you for in a job that needs everything signed in quadruplicates. So, so n-plicates is going to be another dictionary. And what we're going to do for count in count. So notice I'm not going through the birthdays anymore. I'm going to go through the values. And I'm going to count the number of times each of those values appear. So, or I'll just simply say, actually, you know what? I'm not going to change it that much. Yeah, so go for the birthday, go through the keys. Count equals counts birthday. So we get the number of times we saw that specific birthday. Okay, that's what we're doing here. We get the number of times we saw that specific birthday. We get the value associated with that key, the key being the birthday, the value being the number of times we've seen that birthday. We get that count. We sort and count. And then we say, have we seen that number before? If implicates, if count not in implicates, then we've seen it now. So implicates count equals 1. So if we've seen, so in other words, if we've seen somebody who does not have a match, great, put it in there. We've seen one person without a match. Else, if I've seen multiple people with that, then say implicates count equals implicates count plus 1. There we go. And then I'm going to return implicates. Okay. So let's go ahead and comment this out for a bit. Again, before we throw it in a big loop, I'm going to use it to say, here's our birthdays, generate the birthdays. Here's the counts, generate the counts. Let's go ahead and get the implicates now. Implicates is equal to count implicates of counts. Print implicates. And what we see is that when we have 365 people in a room, in this particular sample, we had 69 people having the same birthday. We had 4 people had, 5 people, there were 132 people who did not share a birthday, 369 people who shared a birthday with one person, 23 people who had 3 23 people who had 3 of the same? It's getting complicated here. Let's run this again. There, that's better. So, let's see, count implicates. So, there we go. So what were we counting? We were counting the number of birthdays, right? This total is not going to add up to 365 because this is the number of pairs we saw, the number of triplicates we saw, number of quadruplicate birthdays, and we didn't see any 5-tuplet birthdays there. It's pretty interesting there. So for our last 20 minutes, let's move to a discussion of games. All right. Now, this may or may not be apparent, but I'm a bit of a nerd. And I'm sure that a lot of you are too. And one of my favorite things to geek out about is Dungeons & Dragons. I do like Dungeons & Dragons a lot. And Dungeons & Dragons is played with dice. Now, the reason I'm bringing this up is because for this lecture and the next lecture, we're going to be talking about dice and dice games and different things. And Dungeons & Dragons uses a lot of different dice, right? Dice actually and statistics don't go as hand in hand as you would think. In fact, statistics was not really it was not a very. It was not very well thought of by scientists until like Galileo, did some statistical experiments for money because he needed money. And the statistical experiments he did it on were gambling games because a gambler gave him money. A noble with a gambling habit gave him money to study gambling, so that he could win more money. So it's not. Statistics was seen as uncultured. So statistics was not really a big thing until like people started studying dice games, and that was the beginning of statistics. So I think it's fitting that in intro we are going to be looking at dice games a whole lot. Now, in dice, typically we, most of the time I will be talking about dice in terms of this notation, which is the D notation, which is standard for most role-playing games out there. And I hope it will eventually be accepted by a scientific community if it's not already. But basically it's num D sides. Okay? So in other words, 3d6 means roll 3 6-sided dice. Okay? You're going, wait, sides? Aren't dice 6-sided? And the answer is, most of them are, but not really. Dice are actually, well, let's take a look at dice. All right, here's your standard 6-sided dice. And dice have been around for a while. Look at this. This is Roman dice over here. Hasn't really changed that much. This one's a knucklebones die? That's weird. Here's a bunch of dice from Asia. This is a 20-sided die from Egypt. By the way, that's the way a 20-sided die looks these days. Right? This is the standard role-playing dice. This is your 20-sided die, meaning that you've got your numbers 1 through 20. 10-sided dice, where you've got your numbers 0 through 9, with the 0 typically being a 10. Right? 12-sided die, which is almost never used unless you're a barbarian in Dungeons & Dragons. A 4-sided die, also known as the caltrop, because God help you if you step on that. You thought stepping on Lego was painful, but it does not compare to the pain of stepping on a 4-sided die. Right? So typically, most role-playing games either use just D6s or they use these dice, which are pretty easy to simulate, by the way. It's very easy to simulate throwing a die in Python. So I'll just call this. It's extremely easy to simulate throwing a dice in Python. Dice.py intro, and because we can make one function to handle all of this. So import random roll dice. Roll dice, def roll dice. Okay. Num dice and the sides of the dice. Okay? That's all you really need for most basic stuff. Roll dice and the number of sides. Okay? And what we do is that total is equal to 0. We're going to return total in the end. There you go. And for num dot, so for blank in num dice, for blank in range num dice. In other words, how many times do I want to throw dice? How many times do I want to throw a die? The number of times I have dice. Like if I have 3 dice, I'm supposed to roll 3 dice. I'm going to repeat this 3 times. Total is equal to the current we have plus random dot rand range. If it's rand range, That's a big number. It says the biggest it can be is this number over here. So 1 through sides. Print roll dice. So this will give me so rolling a 1d8, in other words, one 8-sided die, this should give me a number between, this will give me a number between 1 and 8. Side is not defined. Sides. Spelling error is my bane. 3, 6, 8. Roll 2 of them. Give me the total. So this will give me a number between 2 and 16. But it will be centered primarily, but because we're rolling multiple die, it's not evenly distributed. Right? For instance, if I were to roll 6-sided die, that gives me a number from 6 to 36. But getting 36 or 6 is very rare because that would mean I'd have to get all 6s for 36 or all 1s for 6. So 23, 20, 14. Once you start grouping dice together, it stops being a uniform distribution and starts being a random distribution. Incidentally, what I can do over here is show you how these default values work. I can say num dice is equal to 1 by default, and sides is equal to 6. So by default, if I call roll dice and don't provide it with any arguments, it's going to roll a 6-sided die. That's how default arguments work. If I provide one argument, it's going to say roll 10 6-sided dice. Make sense so far? Because I provided the one argument, so it puts it in the first one, which is the number of dice. And then if I put in a second argument, 10d2, a 2-sided die. What's a 2-sided die? That's a coin. It's gonna almost always be 10. Let's see. 1 to 2. Really? Is it not going? Oh, let me check rand range, see how that works. If I got it wrong. Python rand range. Okay. Rand range. Start, stop. Okay. Yeah, I want rand int because it won't include the top number. There we go. 15. We're flipping 10 coins and getting a 1 for heads and a 2 for tails, essentially. All right, and we can kind of see this with, what we're going to use this for is mainly we're going to roll 3d6 for this last portion of class. 3 6-sided die, or actually 4 6-sided die. So the way character generation in Dungeons and Dragons works is that you've got, you have a character and you have 6 attributes. Your strength, which to use, I'll use the tomato analogy, which is popular online, which is strength is how far you can throw a tomato. Dexterity, how well you can dodge a tomato thrown at you. Constitution, the number of tomatoes that you can withstand being thrown at you. Intelligence intelligence is how likely you are to know that a tomato is a fruit. Wisdom is how much you're likely to realize that just because a tomato is a fruit, that shouldn't be put in a fruit salad. And finally, charisma, which is your ability to sell a tomato-based fruit salad. And the answer to that is just simply slap the label salsa on it, add heat, and call it a day. Okay, so the way you generate your statistics in Dungeons and Dragons is to roll or at least for the way you do that in Dungeons and Dragons is you roll 4d6 for your stats for each of the 6 stats and drop the lowest die. In other words, so we drop So we take the smallest and drop it. So what we'll do is that we will just simply focus on rolling a bunch of d6s. And then we're going to look at the statistics to see what the average statistic is, what you get from doing this creation method. Right? What is the average of a stat? So def, roll 4d6, drop 1, or drop lowest. So we need to roll 4 6-sided dice. Then we got to drop the lowest. So it's not enough for me to get the total. What I should need to roll these one at a time and actually keep track of what I'm rolling. So rolls is equal to an empty list. What I'm going to do is say for blank in range 4, because I'm going to roll 4 of them. Roll dot append for the, we're going to append random dot rand int 1 through 6. So we're going to add all those numbers to the list, okay? And then it's actually fairly straightforward to just simply add them up but subtract the lowest by using just stuff built into Python, right? It's a list. So there's a sum function built up into Python, which says add up all the numbers in here. Now that adds up all 46, but what we really want is 46, but we need to subtract the lowest roll out of that, right? So that's also very easy to do, because what we'll do is simply say min rolls, right? Makes sense? Add them all up, and then take the smallest one of them and subtract it out. So roll 46, drop lowest. And let's see. So first off, I forgot to put in the colon because I always forget to do that. Print. And now 11, 15. So the highest thing you can get is an 18, right? That's pretty nice. Getting an 18 is like being on the top of your game. 3 is basically not good at all. It would be terrible to have a 3 in any stat. But let's see but now that this works, let's see how well we can, let's take a look at counting statistics. Right? So def, so let's not even bother making a function for this. Let's just make a main function and just and do our standard 10,000 trials of this. So what we'll do is we'll do our stats is equal to a dictionary, okay? And what we'll do is that we will, for blank, and what we're going to do is we're going to roll 10,046 drop lowest trials, and then we're going to see, and we're going to count up the total amount and see how that distributes out. So for blank in range 10,000, all we have to do is say roll is equal to roll 46, drop the lowest. So that's our roll. And then say if roll in stats Okay, so if the roll is in the stats, well, actually, let's use this way we've been doing it for the entire class so far. So if we've not seen that roll yet, then we've seen that roll once. Else, stats, the number of times we've seen that roll, really should have called it counts. Stats roll plus 1. So we just simply roll this 10,000 times and we're seeing how this turns out. So we can print out our dictionary, but that's not really going to tell us like good information. Also would help if I called main. So we see that basically, so we do see that it's very rare. 8 times out of 10,000, you got that unlucky 3. With the 18 though, you got 160. Now why is it that it's much more skewed to the higher numbers? Why is there 160 of getting 3 sixes, but only 8 times we got a 3? And the reason for that is because it's 46. You're not rolling 3d6. You're doing 46 drop the lowest. So in order to get a 3, that means you had to roll 4 3s, right? 4 3s, and then you threw out the lowest, and you were still left with, 4 1s. You had to roll 4 1s. So you throw out that 1. You throw out one of the 1s, you're still left with 3 1s, so you get a 3 total. On the other hand, for an 18, you either need 3 6s and a 1, 3 6s and a 2, 3 6s and a 3, 3 6s and a 4, or 3 6s and a 5, or 4 6s. So there's 6 different ways you can roll an 18, right? Because it's dropped the lowest. So that's why it gets skewed. And we want players to have good stats because nobody wants to have a 3, but lots of people want to have 18. That's exciting. So so let's go ahead and see what their percentage is. Right, so what happens if I tried to sort a dictionary, by the way? What if I did sorted stats? That gives me the, what I did sorted stats dot items. Not iterable. So what I'm going to do is I'm going to go through every item in my stats. And I'm going to replace the count I've seen it by the average. Or maybe I'll just go and create a different one rather than destroying it. Averages, or let's call it percentages, is equal to a new dictionary for for roll in stats if roll not in percentages actually it's not going to be in because there's only going to be that many rolls. Stats.keys percentages roll is equal to stats roll, the number of times that roll occurred, divide by 10,000. Print percentages and there's your percentages that they occur. And now let's just, as our final act, let's make it just slightly more pretty to read. For per in percentages dot keys sorted. So now we're going to be able to go through it sorted. Print per percentages per sep equals tab. And there we have statistics now of how often, of what the percentage, 46. If you roll 4 six-sided die, drop 1, these are your chances of getting each of these. Your percent chance of getting each of these. You got a 1% chance of getting an 18, but only a 0.05% chance of getting the worst roll possible. So it really does favor you. And this is kind of the power of Python and dictionaries. You get this ability to do statistics really easily. And sometimes doing statistics is no more than just pretending to roll a bunch of dice. Sorry? It's pretty good. Means to +1 to that roll if it's in the stat. Not bad.
does this keep giving me an error with the return?
What,
It's been doing it all class.
what is it saying?
I don't know, it just said invalid syntax.
It might be an issue somewhere else when it says invalid syntax. Right, run invalid syntax where it says return over there. For I in range 4. Oh, you're missing a parenthesis on the end.
Oh, my bad.
That's what the invalid syntax is.
Okay, thank you.
Oh.
Give me my code.
Yeah, give me 1 second to stop recording because I'm sure you don't want your scores to appear online.